Perfect. So a quick recap of what we did yesterday. So we realized the ideal quantizer. So over here we saw a 3-bit digital quantizer, and this was ideal because the steps are ideal with ideal width. So the width of the step is perfectly similar, and there is no offset error. So we said that the width of each range, so this is the range. So we have from 0 to Vref, and our input voltage will lie between this range. So whatever the input lies within this range, wherever it will be either in one of these either ranges, and the width or the step size will be basically Vref divided by 8. So because it's going from 0 to 7, so it's Vref divided by 2 to the power 3 because it's a 3-bit quantizer. So then we talked about some non-idealities. So those were due to V offset. Then we talked about the gain error where the width increases due to the gain. Then we saw that not all steps are uniform. So to quantify this errors, we came across some quantities such as DNL, which is differential non-linearity. So then we saw that talking about differential non linearity, it is for a code K, and it is describing what the error at that particular local code. So let's say if we take code 2, so it will talk about this local code 2, and it will describe the non-idealities over there. So then so in this video, I would like to start again with a non-ideal quantizer. So we can see that the widths are not uniform throughout the steps. Again, we have 2 to the power 3 bits. So we have 3-bit quantizer. Then we can also see a missing code over here. So we have steps, but at this code, we don't have any step. So this is a phenomenon of missing code. So when we talk about the ideal quantizer, which we saw in the beginning over here, so then as we described the DNL, so we can say for ideal quantizer, every code of the ideal quantizer, so basically this is non-ideal, but every code of an ideal quantizer will be having a DNL which is equals to 0 because there are no errors or no non-linearity. So the DNL is 0 for ideal quantizer for every code or every step. So when we talk about non-ideal quantizer, so let's take code 4. So code 4 has a width which is lesser than the step or the least significant bit. So that's the mean or average step size, or basically that's something which is ideal step size when we design mathematically. So when we saw LSB, so um, let's say step 4, I mean not let's say, it's actually we can see that the step 4 is lesser than the LSB, least significant bit. So the code 4 will be having negative DNL, whereas code 1 has a width which is greater than the LSB, so it will have a positive DNL. But in the case of code 6, the code is missing. So the width is missing. So basically the DNL for code 6 will be -1. So we will come to this soon. Like we'll derive the situation for this and we'll understand why it is -1. But as of now, let's take it as it is that for a missing code, the DNL is -1. Now that we have talked about the differential non-linearity, so we'll talk about another term which is integral non-linearity. And while we describe it, so basically integral non-linearity tells us about how far the transition voltage. So transition voltage is basically it is going from this step to this step. So this is our transition voltage. So let's take V4. So basically K is representing all the numbers. So let's say Vk or K equals to 4. So our V4 is basically this voltage over here. So this is our transition voltage for V4. So basically for any number or for any code K, how far the transition voltage Vk is from the ideal transition. So over here, if we plot the ideal transition, so it will look like this. So then basically the integral non-linearity, it will tell us about how far the transition voltage for that Vk is from the ideal transition. So ideal transition this. So we are basically talking about how far the width is. So then we can refer to this figure over here. So we have, let's say we have a code K, and then if we have the code K, then this is the Vk, right? But when we talk about the ideal transition, so basically ideal transition will lie at K times delta. So what is delta over here? So delta is a LSB or a bit size or ideal step size. So that's the LSB, ideal LSB. So then K times delta will be the voltage for that K code. So this is the ideal, right? And how far the transition is from the ideal one. So basically we have Vk, which is our non-ideal, and we have delta K, which is our ideal. So the difference between those two is being told by integral non-linearity. So, but also we have to take like divide it by the step size itself to normalize it, because we are talking in normalized terms over here. So in case of DNL also we normalized it. So in case of INL, which is integral non-linearity, we have to normalize it with the step size itself. So we have the difference, right? So we have Vk minus K times delta divided by delta, which is representing our integral non-linearity, which is again a function of K, because we are talking about kth code. So it's INL of K. So if we represent it in a graph format, so basically this curve or this line or this slope will give us the stair. Let's say that this is a stair or the staircase. So this will go give us a slope of that staircase, which is ideal, and this curve will basically give us for non-ideal, which is basically this one. So when we take the, like we see how far the transition voltage is from the ideal transition, it gives us the INL. So similarly, for Vk, we derived the INL to be this value. So then INL for K plus 1. So for the next code, we have again Vk plus 1 minus K plus 1 times delta divided by delta. So then when we take the difference between those two INLs, basically two consecutive INLs, then we have INL of K plus 1 minus INL of K, which gives us, so basically this quantity minus this quantity, which comes out to be this, and in the end which gives us DNL at K. So basically what we are talking about over here is INL is giving us a bird eye view over the distribution of quantizer, whereas DNL is talking about the local nonlinearity. So let's take a case. Now let's discuss a case where we plot the kth code on x-axis and the DNL on y-axis. So then when we plot it, we have some sort of this kind of curve. So this is not continuous. There are again samples, but all samples, let's say they are so close to each other that it looks like a curve. So for just for simplicity, I have drawn a curve, but it simply is looking, if we zoom it out, it will look like this, where it goes from minus 1 LSB to 1 LSB. So it should lie between LSB for a step to be significant. It should lie between minus 1 LSB to 1 LSB, right? Because that's what we are normalizing with. So this will probably, like if we zoom it out, will look like this, where um, yeah, where this code has a width which is much higher than 1 LSB, right? And this code has a width much lesser than 1 LSB. So then if this is our code, let's say if this is our this code, so if we have this LSB, then its width is much higher than LSB. And talking about this code, so again, if we have this LSB, then its width is much lesser than the LSB. So from this, we can say that we have a missing code for -1 LSB. So if it goes to -1 LSB, so basically it will be 0. The width will be 0. So it will be the case where we have the missing code. So that's how when we talked about a missing code earlier, so we have a missing code for the value -1 LSB. So then like we will take an overview. So basically DNL is giving us a location, or basically it will talk us, like it will give us the local variation in the slope of staircase, and INL will basically give us a bird eye view of the entire characteristic. So sometimes probably due to a missing code or some other reason, we will get to see a non-monotonic staircase. So basically this is a monotonic staircase, and where it somewhat goes like this. So this is a non-monotonic staircase where these two levels are same. So for a sample which is lying under this level, or a sample lying under this level, will get quantized to a same code, or same amount, like same number of, or same digital word. So this is a non-monotonic staircase, and basically if the mod of DNL is less than 1, so that's what, if DNL is between -1 to 1, that this means the same thing. If mod of DNL is less than 1, then all steps exist. And if all steps exist, then there is no missing step. And basically, all steps are between 0 to 2 LSB. Why 2 LSB? So basically, magnitude is 2 LSB, right from -1 to 1. So basically, all the steps are, all the step sizes are between 0 and 2 LSB, and we can ensure the monotonic characteristics because all the steps are existing when we apply this condition. So many times an analog to digital converter is embedded inside a feedback loop, and it's a big problem to have a non-monotonic characteristic like this. So at that time, we have to make sure that the mod of DNL is lesser than 1 for all steps to exist. So then now we have this ideal staircase, and when we implement the quantizer, we have this actual staircase. So basically, how do we calculate, or how do we talk about DNL and INL? So to come across the values of DNL and INL, we need to first fix the V offset error and gain error. So basically gain error is nothing but the LSB size is not equal to the ideal LSB size. So that's what a gain error is, right? And to remove the gain error, we need to come up with an average step size. So these are our steps. So we need to, so for all these steps, the average step size will be same, which is actually the ideal LSB. But now in actual case, or in non-ideal case, we have like the LSB size is not equal to the ideal LSB size. So then we need to come up with the average step size. So one way of measuring the average step size, there are several ways, and you can do it using several methods. But one way of measuring the average step size is to find the range of the codes. So basically from like, this is the range of the codes, or VREF, and divide it by the number of codes. So then we have the range basically from 1 to 7, which is 7. And then we will get, let's say, V1 and V7. So when we minus V7 minus V1, basically when we take this voltage and when we divide it by number of codes, then we'll basically get average LSB size. And instead of using ideal LSB size, now we can use average LSB size to resolve the gain error. So as of now for this video, um, that's all for this video. In the next video, I'll start and tell you, like, I'll finish it off in 1 minute, that what is like what we do to resolve the offset error. It's very simple. And then we'll start with the noise in quantization. So as of now, that's all from my side. Thank you. If you have any doubts, let me know.